So if we have the observations x sub 1 through x sub n from some random sample that follows a Poisson theta distribution, and we want to determine the maximum likelihood estimate of that theta, how can we go about that? Now, before we get into this right here, you should notice that this is going to be very similar to my daily problem from yesterday, daily problem 10. So if there's anything you miss here, you should take a look at that guy because I might go into more detail in that one. So again, we're just going to start with our PDF, right? So remember that the PDF of the Poisson theta is going to be, theta to the power of x times e to the negative theta divided by x factorial, right? So, in some textbooks, the likelihood function will totally ignore all of those factorials, and you can totally do that. Any like constant, get rid of it. Who cares? But I'm just going to show you it here because when we do take the derivative, it goes away. So that's why you can get rid of it earlier if you'd like to do that. So our big L of theta is our OG likelihood function, right? That's just the product over all of our observations of our PDF. And then if we take the ln of that, the natural log of our big L of theta, we get little l of theta, which is the sum from I equals 1 to n of negative theta plus, our observation xi times ln theta minus that weird factorial thing I was talking about earlier. And now we want the maximum, so we have our likelihood function, and if we take the log or we take the regular one, it doesn't matter. We can take the derivative of either one of them, as they both preserve, where the maximum will happen. It's the same point, so it's irrelevant. We just use the ln because it's easier to take the derivative of that. So we take our partial derivative and we set that equal to 0, and that gives us this line here, where our sum looks like that because, remember, when you take the derivative of ln theta, you're going to have 1 over theta. So since we're multiplying that by xi, we have xi over theta. And then the derivative of just theta is negative 1. And our other guy doesn't have theta, so he disappears. And then when we set that equal to 0, right, we can move our negative 1 to the other side. But don't forget, you got to multiply by n, right, because it's part of our sum. So we have, that sum xi divided by theta equals n, and then we can multiply that by theta. So then we have n theta equals, the sum over all of our xi's, which then implies that theta equals x bar n. So that should be pretty standard, and that is our maximum likelihood estimate. But, don't forget, you got to check that it's right. So to check, you just take the double derivative, again with respect to theta, and again partial. So I'm taking the derivative here in this last line of our sum that we got in the previous line. So all I'm doing is I get negative, theta squared divides xi. And then I'm doing the same trick that I did last time, which is where, since I'm summing over all of my xi's and x bar is really just that sum divided by n, I can just do, this whole sum thing equals n times x bar. And the reason you do this is so that when you plug in your MLE, which happens to be x bar, that's no coincidence, it's easier to just show, that we're less than 0 always, which is all we need to show. Yeah, and then we're done.